Morning. Hello to all of you joining us today in this really crazy weather, both here in person and online. My name is Donghyun Cho, and I'm a senior researcher on the Security and Technology program here at the UNIDIR. I would like to start by thanking you for participating in today's multi-stakeholder dialogue on quantum technologies and their implications for international peace and security. Of note, this event was funded by the European Union as part of the UNIDIR Security and Technology Program, which is supported by the governments of the Czech Republic, Germany, Italy, Netherlands, Switzerland, and Microsoft. So as a starter, an increasing number of member states have flagged in the Open-Ended Working Group, or OEWG, the potential new threats emerging from quantum technologies. In his annual report on current developments in science and technology and their potential impact on international security and disarmament efforts, the UN Security General also highlights the potential risks emerging from quantum technologies. Despite this increased interest, little discussion exists on this topic, at least among states. To further unpack this complex issue and understand the possible effects and consequences of these advancements in quantum more broadly, UNIDIR Security and Technology Program organizes a multi-stakeholder dialogue on quantum technologies today. So today's panel discussion will introduce you to quantum technologies in a broader term and the challenges they give rise to, and is structured into three parts. First, we will examine an overview of the technology and current development behind the quantum technologies, first of all. And in the second session, we will examine their impact on international peace and security. And lastly, in the closing remarks, Ms. Marieke Hood, Executive Director, Impact Translator, Geneva Science and Diplomacy Anticipator, or GESTA, will introduce the Open Quantum Institute. Each speaker will deliver a presentation, and we will open the floor for Q&A after their last presentation. So if you'd like to take the floor after the last panel presentation, please raise your hand, and we'll give you the floor to speak. And for those joining us online, please feel free to type your questions into the chatting box throughout the panel discussion. Please make your questions as specific and clear as possible, and indicate to which panelist the question is addressed. That will be really appreciated. So without further ado, please let me first introduce our first speaker, Dr. Geraldine Hack, Assistant Professor, Université de Genève. Dr. Geraldine Hack is a theoretical physicist, expert in quantum thermodynamics and quantum transport in the nanoscale devices. After a PhD in Geneva obtained in 2008 and several postdoctoral stays in Berlin and Grenoble, she received in 2018 a PRIMA grant from the Swiss National Science Foundation to start her own research group, and she is now a permanent researcher at the Université de Genève. Her research focuses on understanding how quantum properties can be exploited to develop quantum technologies for quantum information processing and for quantum sensing. Geraldine, over to you.
Thank you. So I will just move to see also. Do you hear me? Yes? Okay. So good morning. Thank you very much for organizing this meeting. It's a great pleasure to be here. So my name is Geraldine Hack. I work at the University of Geneva, as Donghyun introduced. And as she said, we hear more and more about quantum technologies, and it's really important to understand what they are, to understand what role they can play, and here in particular, we are interested in, diplomacy, and this is your field of expertise. But so on my side, I will introduce you the physics which is behind quantum technologies. So just to introduce a bit more myself. So I work at the University of Geneva. Here, so you see, we have different types of activities, fundamental research, more applied physics, theory, and experiments, okay? Our activities, now, they are encompassed in a Geneva Quantum Center that you may have heard about. And it includes the activities of 3 departments at the University of Geneva, the Department of Applied Physics, of Quantum Matter Physics, and Theoretical Physics. And 20 research groups participate to that Geneva Quantum Center. Of course, okay, with the importance that quantum technologies take now, it's more and more important to develop a quantum ecosystems, because now quantum is not only a topic of interest for universities and academic people, but of course for industry, for companies, for government institutions. And so just to mention some of the names which are around here in Geneva and in Switzerland, there is also, of course, the CERN, which is developing quantum activities through its initiative Quantum Technology. There is GESDA, and we have Marieke today here. There is HES, which is also part of, teaching and teaching young people. There are companies, for instance, Idecantic, which is one of the leaders in quantum technologies for quantum secure communication, the SIGS, Swisscom. And in Switzerland, there are other quantum centers with which we interact closely, especially at EPFL, at ETH, and in Basel, but of course all the other universities, Fribourg, and some national research program. So this is a bit the context of our research. Okay, now just to introduce a bit the physics and the topics. So we can find quantum technologies in different fields or different applications, no? I think we have all heard about the development of quantum computations and simulations, and this is very useful for chemistry, for material science, and for high-energy physics. Here, of course, the research has been, there has been such a big development in the last 20 years that now there are commercially available chips for quantum computing. And here I show you 3 examples made by companies, IonQ, IBM, and Intel, and they are all based on different platforms, and I will come back to that. So that's one big direction, of course. Another one is to develop quantum cryptography protocols and quantum communication. And here, why, and I will come back to this, why is it so interesting to have quantum mechanics playing a role, is that it will provide ultimate security protocols. And why do we call that ultimate security protocols? Because the security then does not come from the complexity of a mathematical problem with which that you could break if you have a sufficiently powerful computer like a quantum computer, but the security comes from physics itself. So then that's why it's called or sometimes known as ultimate security protocol. And so there are also companies which have developed commercial products. So Idecantic, based in Geneva, WeLink, which is a French company. Another very important direction, which was mentioned in the introduction, is quantum sensing. And here I will also explain you a bit why quantum mechanics provides an increased sensitivity, allows us to build nanoscale probes, and also, very importantly, non-invasive detection processes. And here you can imagine how important this can be for instance, medical applications. So there are also different companies which exist now. And of course, another very last important direction is quantum materials, because all these technologies now are based on physical platforms. And so this is possible because we have more and more control on how to control a single atom, a single photon, a single electron, or atomic layers. And this allows us to develop new materials designed on purpose for a specific task. And so this is also a very important direction. So all this you know. Now let us be a bit more precise. These quantum technologies work because physicists in lab or in companies know they are able to manipulate different physical platforms and their properties. And here is a picture now which summarizes a bit the different platform with which people are working, scientists. So superconducting qubits, trapped ions, spin qubits, NV centers, cold atoms, nuclear magnetic resonance system, photonic platforms, topological systems. So you may know some of the words or not, but what I would like now to insist on is that, in fact, all these platforms, they manipulate very fundamental individual carriers or particles. And here are three examples. Spin qubits, you play with electrons. Cold atoms, as the name says, you play with individual atoms. Photonic platforms, you manipulate photons. And now, experimentally, the expertise has been so much developed that they are really able to control the emission of a single photon or the detection of a single atom. And that's why quantum technologies are today possible. So now the question, why quantum mechanics is expected to provide an advantage? Why are we so excited about quantum technologies? And in fact, I think there are three main fundamental properties that explain why quantum technologies are so interesting. And so let me explain you a bit these fundamental properties. First is that when you start working in the quantum world, then you're, for instance, this is a drawing of a sketch of an atom. In fact, you have the energy quantization of your system. It means that your physical system, whatever, an atom, a molecule, or whatever, cannot take all possible values for energies, but can only take discrete values. You may have heard about the Bohr model, which was developed at the beginning of 20th centuries, and this was really the origin of the name of quantum mechanics. It means that you think in terms of quanta, something is quantized. So energy is quantized, the charge, electrical charge is quantized. And so this is, for instance, here I draw the lowest two energy levels of an atom. And you have to set a reference. And for instance, the lowest energy level has an energy 0, and the first excited level has an energy E. And then what happens is that your physical system, very concretely, it can be in its lowest energy level, or it can be in its first excited level. And this we can label, for instance, the state of the system by a 0 or a 1. Okay, that's just a notation that I will use after, so just to make the notation clear. So that's the first property. The second one, which is very important, is quantum covariance. Quantum covariance, it means that, okay, maybe let me just come back to before. You see, here I have two states for my physical systems, and this should remind you of a classical bit to encode information. For a classical bit, it takes a value either 0 or 1, okay? But it can only take these two values, either 1 or the other one. In quantum mechanics, what we have now is that our physical system can be in a superposition, and it's called a covariance superposition of two states, the state 0, for instance, and the state 1. And if I write this mathematically, it's written like this, that it's in a superposition. And here you start, this is at the basics, at the basis of the advantage that is exploited for quantum computation, that you can encode information in a much more powerful way because you have all the possibilities. Your system can be with 30% probability in state 0 and 70% in state 1. But what is really important in quantum mechanics, and what will explain the following, the rest, is that if one measures a quantum system, then you will only, it's a real measurement, you perform the measurement with a macroscopic apparatus. And then you will see that your quantum system is either in state 0 or in state 1. But you cannot measure that the state is both in 0 and 1. This does not make sense. So that's really important because sometimes there are some confusion, and I think you probably know the Schrödinger cat, which is dead and alive. Okay, it's a picture, but it's a bit confusing because it's not true that the cat is dead and alive. If you open the box, the cat will be either dead or alive. It's just when you don't look at it, you don't know in which state it is. But a quantum system, as soon as you look at it, you perturb it and you only detect a specific state. Okay, and that's very important. So that's for quantum coherence. And quantum coherence is really this ability of these individual quantum systems to be in a superposition of two states. It can be two energy states, it can be the polarization of a photon, it can be the occupation of an electrical charge, it can be many things. And the last key properties is quantum correlations. And here it's in the form of entanglement, for instance, which you may have heard about. I will explain that a bit later because it requires a bit more technical details. So these are the three main features in quantum mechanics. Now, why is quantum coherence so special? Because right now I just told you that the system can be in a superposition. Okay, but why is that interesting for quantum technologies? So let us think about an easy experiment, which is a double slit experiment. A double slit, it's a screen with two slits, and you send something, and then you observe something on a screen. Okay, so let's do a Gedanken experiment. If I do it with tennis balls, and so I have large enough slits, then if I send tennis balls, of course I will have on the screen two packets which are well localized in front of the two slits. So that's easy. And this is what will happen in general with particles. Now, what is the output of the experiment if I do the same with water waves? Okay, we all know these experiments. If you throw two stones in water, what you see is an interference pattern. And this is illustrated here. You have a source of light or waves, And then, of course, you have this interference pattern, which means that on the screen, I think it's easy to understand, you have a maximum, minimum, as a function of the position. And these two behaviors are typical from a wave-like behavior or a particle-like behavior. Now, what is special about quantum objects? For instance, electrons. So from high school, you remember that the current is defined as the number of electrons per unit times. Okay, it's a flow of charged particles. So naively, you think, okay, my electrons should behave more like my tennis balls, But if I do the experiment, it's not me who did it. It's a research group in Japan, so in '89. And here are different pictures of the screen as a function of time, you see. at short times, you see the individual dots, which are the individual electrons. But as time flows, what you see is exactly the interference pattern that you would obtain if you would have sent waves through the double slit experiment. And this is really due to the quantum mechanical properties or description of an electron that at the quantum scale, which means when you are at sufficiently low temperature, sufficiently isolated from the environment, you cannot describe your quantum object as just a particle or just a wave. It's a wave function, and depending on how you measure it, and this comes back to what I said before, when you measure a quantum system, you change its state. If I do a double slit experiment with an electron, I will put in evidence the wave-like behavior of the electrons. But be careful, if I do another experiment, I will put in evidence the particle-like behavior. Okay, but in a given experiment, I can only evidence one of the properties. It's as before, I can only see whether the cat is dead or alive, but not both. Okay. Now, what happens is that if I measure, for instance, I put a measurement apparatus here and I measure the slit. Well, I put an observer such that I know whether the electron went through that slit or the other one. Then what happens is that I perturb the quantum state, I destroy this quantum coherence properties, and the interference pattern will disappear. Okay, and this is one of the key features why you can do sensing and why it is an advantage, because a very small perturbation of your quantum system, and when I mean perturbation, it can be a very small and weak interaction of the quantum system with something else, will provide me information about the state of the other quantum system, because it will affect my quantum system. So this is, for instance, something which is used for quantum sensing. Now I can go to quantum correlations. So to introduce quantum correlations, I need to not only consider a single electron or a single photon or single atom, but I need to consider at least two. So now I have, for instance, two photons, photon A, photon B. And what I consider is a new system composed of two photons, for instance, which are in a lab, okay? In classical physics, if I take the notation that I introduced before, the state of this bipartite system, will be just the product, if you want, of the state of system of photon A and the state of photon B. And this is a classical description, and it's valid under certain experimental conditions. Now what happens is that in quantum mechanics, you can have a very specific state. If you are careful about the labels, it means that on one part, I have my photon A in state 0, photon 1 in state 1, and then the reverse. And you can try, you can play at home, there is no way to rewrite this expression as something belonging only to A times something belonging to B. It's not possible to separate these two systems. And this is a very specific type of correlation that you cannot explain, that you cannot demonstrate with classical physics. You need quantum mechanics. And this one is, for instance, the Bell state. And this was the topic of the Nobel Prize in 2022. So now, just to explain you why it can be useful for instance, for secure communication, is that this state, it's not only possible to have it in a lab, but it's possible to separate the two photons very far away, and they will keep these quantum correlations. So because they keep these quantum correlations, it means that as soon as I do something of photon A, I will know what is the state of photon B. And this is sometimes known as spooky action at a distance. And this was something Einstein at the beginning has some trouble with. So if you put a communication channel between these two states, which are quantum correlated, which are entangled, then if you have any spy that would like to capture or to spy some information which is transmitted between these two labs, then this will disturb for sure the state shared by the two photons. And this is at the basis of all the the protocols for secure communication. And that's why is the ultimate security, because it really comes from these quantum correlations between the two parties. So with that, I conclude here. So yes, quantum technologies, for sure, they do provide advantages for secure quantum communication, quantum sensing, quantum computation. What is really important is that all these advantages come from fundamental quantum mechanical properties that I introduced to you. Quantum technologies can be developed because right now there is a very strong interplay between fundamental research, applied research, and development of commercial products. And I think in the history of technologies, it's the first time that there is such a close connection between academy and industry, and because it's so technical that all the partners must be part of the same game at the same time. And hence the importance of the quantum ecosystem, and hence thank you again for your invitation.
Thank you very much, Geraldine. I think you just really mentioned importantly to get better understand three main fundamental quantum mechanical properties, which could be a really starting point for the further discussion during our today's dialogue. Thank you so much.
Thank you.
And our next panelist is Ms. Janna Malako-Smith, and she is a non-resident fellow with the UNIDIR in Geneva here, and a senior associate with the Aerospace Security Project and Strategic Technologies Program at the Center for Strategic and International Studies, or CSIS. Additionally, she is a visiting fellow with the Carnegie Council for Ethics in International Affairs and a fellow with the Army Cyber Institute at the U.S. Military Academy at West Point. Previously, Malako-Smith was an assistant professor in the Systems Engineering Department at West Point and a professor of cyber warfare studies with the U.S. Air War College. So the floor is yours, Janna.
Thank you. Good morning, ladies and gentlemen, and welcome to the bizarre world of quantum, or as the physicist Albert Einstein described it, spooky. Quantum information science and technology could revolutionize the field of computing, enhance sensors with the ability to detect ultra-sensitive disturbances in the environment, whether it's vibrations or temperature, as well as augment intelligence, surveillance, and reconnaissance operations for military capabilities, and potentially enhance as well as challenge the security of communications networks. My remarks today, however, will primarily focus on quantum computers and the associated cybersecurity risks around this technology and that it poses to information communications technology. So what is a quantum computer? It's a highly advanced computational device that uses quantum systems. These devices compute on atoms using information storage units called qubits, as opposed to classical bits. Quantum computers utilize a technique called amplitude amplification, and that enables it to perform searches in unstructured databases exponentially faster than classical digital computers. Additionally, these advanced computers could potentially solve certain mathematical problems, such as prime factorization or discrete algorithms, to run code-breaking attacks against modern cryptographic protocols like public key encryption and digital signatures. And this is alarming for several reasons, because these security protocols, which secure our day-to-day internet-based communications and financial transactions, could be compromised. Furthermore, quantum computers could potentially decrypt classified information stored on encrypted devices, allowing adversaries access to sensitive defense and intelligence information. To be clear, quantum computers are in a relatively early stage of development, with many of the advancements being driven by the private sector, and we'll hear more about that later today. However, states are increasingly prioritizing investing in this area. Just to give a few examples, France aspires to be one of the world's leaders in quantum and supports the European Union's Digital Compass project to produce a domestic quantum computer by 2025. Germany also envisions leading the quantum innovation race here, according to its 2023 Quantum Technologies Action Concept, which sets forth a strategic framework and pledge to invest 3 billion euros in developing a universal quantum computer by 2026. Additionally, the Russian Federation pledged to invest 800 million in developing quantum technologies in its roadmap through 2025. Across Europe, the European Joint Commission on High Performance Computing announced plans to construct 6 sites for European quantum centers in the Czech Republic, Germany, Spain, France, Italy, and Poland. But to date, no member state has developed a large-scale, all-purpose quantum computer capable of breaking modern asymmetric cryptographic protocols like RSA or the Diffie-Hellman key exchange. However, it is not a question of if the necessary quantum hardware and software capabilities will be developed, but when. States are engaged in a strategic game of power and stability to build one, which is why I purposefully selected the chessboard theme for today's presentation. As you can see, the chess pieces outlined here on the stand. Let's talk a bit about the cybersecurity risks now. The cybersecurity risks are already here today. Speaking to that concern, I will be unpacking what are harvest now, decrypt later attacks. We'll touch upon that in just a moment, as well as post-quantum cryptography. Bottom line, the focus of my remarks today is to help inspire a dialogue amongst different stakeholders about what should be done as a collective in considering multilateral policy as a vehicle for the potential new threats emerging from this fascinating technology and the threats that it poses to critical infrastructure as well as information and communications technology. Apart from the code-breaking concerns, quantum computers could enable advances in machine learning, a subfield of artificial intelligence, and such advances could spur improved pattern recognition and machine-based targeting in military operations. In turn, this could potentially enable a new generation of lethal autonomous weapon systems, or as some analysts have suggested, weapons that are theoretically capable of selecting and engaging targets without the need of manual human control. And on that cheery note, I've been asked to prepare some remarks on the basics of quantum mechanics that are both informative and entertaining. And I intend to do exactly that. This presentation was designed to have a little bit of everything for everyone, from a game of chess to ancient Greek philosophy, mystery, and later on a dramatic reading of Shakespeare. But more on that later. Lastly, I wish to thank my outstanding research team for their support, Cadets Christopher Conan, Connor Leggett, Riley Hoyes, Jason Ingersoll, and Lieutenant Christina Hune at West Point, the U.S. Military Academy, and also thank UNIDIR for the honor to present today. So let's begin. According to the Grand Chess Master, Jose Raul Capablanca, to succeed, you must study the endgame before anything else. And for us, understanding the endgame of quantum computers requires first a mastery of the fundamental concepts in quantum mechanics. So together, let's focus on how certain quantum phenomena could enhance information technologies, for example, advancing discoveries in machine learning and improving the ability to run simulations and advance material science discoveries. Next slide, please. Thank you. Please allow me to explain the difference between bits and qubits and why this is significant for computing power. Regular digital computers encode information in bits that can represent a binary state of 0 or 1. So let's imagine when I hold the chess pawn piece like this, it is in a charged state of 1. And when I invert it, it's in an uncharged state of 0. So Binary logic, 1, 0, 1, 0. Contrast that now with a quantum computer that can encode information in qubits. A qubit exists in a continuum of states at the same time. Superposition refers to this ability of a quantum system being able to exist in two or more states simultaneously, and we heard about that earlier from Professor Geraldine. Now, if I have one qubit, you can imagine it equaling two states at the same time. And if I have two qubits, imagine 4 states at the same time. And if I had 3 hands, you would imagine 8 states at the same time. Thus, the power of quantum computers increases exponentially with the addition of each qubit. Regular digital computers apply an algorithm 1 input at a time, but a quantum computer applies the algorithm to all inputs at once. And that's the beauty of superposition. Also, thanks to parallelism, quantum computers could theoretically break modern asymmetric cryptographic protocols like RSA and the Diffie-Hellman key exchange, as well as compromising digital signatures. Quantum computers could potentially be leveraged to decrypt classified information stored on encrypted devices as well, allowing adversaries access to sensitive military and intelligence operations data. Entanglement describes a condition related to this in which 2 or more quantum objects in a system can be intrinsically linked such that the measurement of one dictates the possible measurement outcome of the other, regardless of how far apart these 2 objects are in our system. So the qubits are communicating with one another. And quantum key distribution networks, as seen in the case of China in 2017 with Misius. There's also the matter of decoherence. Due to the highly sensitive nature of quantum states, bless you, which can be disrupted by small disturbances in the environment, like movement and changes in temperature, both superposition and entanglement are difficult states to maintain for prolonged periods of time. These environmental disturbances cause quantum systems to act more like classical systems in that sense, where it collapses into a known state of 0 or 1. Let's move on now, next slide please, to discussing the cybersecurity risks behind this. If the endgame on our chessboard is developing a large-scale, all-purpose quantum computer capable of breaking asymmetric cryptographic protocols, then part of our middle game strategy, let's say, is the harvest now, decrypt later cyber threats. Harvest now, decrypt later cyber attacks refers to a scenario where malicious actors exfiltrate and store encrypted data on an adversary today to then decrypt it once we reach that point of developing post-quantum cryptographic algorithms. Now, these threats intentionally exploit delays with implementing more advanced security protocols. Imagine this. Even if country A were to manage to transition 100% of its critical infrastructure to post-quantum cryptographic algorithms by 2025, all of country A's data that was stolen in the years prior during country B's harvest now, decrypt later cyber attack campaign is lost. In essence, once you've had those chess pieces fall, you can't retrieve them. Scientists as well as policymakers are slowly preparing for that tipping point, which I dramatically demonstrated here, in cryptography. And this forum is an opportunity to begin generating a dialogue around that discussion. Now, to make sure that we have a solid grasp of the scientific concepts that I presented thus far and understand the geopolitical concerns around this, I've decided to take some creative liberties here in developing an educational and comedic parody of Shakespeare's play Macbeth, but with a quantum physics twist. So if you are able to capture the academic humor in the following dramatic reading, that shows you are tracking the main concepts that have been presented. Without further ado, ladies and gentlemen, I present to you Quantum Macbeth. Is this a qubit which I see before me, existing in a continuum of states? Come, let me measure thee. I have thee not, for measuring collapses thy state to a binary form of 0 or 1. Thou art sensitive to environmental disturbances, such as vibrations, leading to thy decoherence. But If 2 or more qubits can be intrinsically linked, praise be to the powers of entanglement, would not the measurement of one dictate the possible measurement of the other, regardless of distance? Thou marshallest me the way that states and private industry are going towards quantum supremacy, speed, and power. But if transitioning to post-quantum cryptography were done when 'tis done, then 'twere well it were done quickly. For tomorrow, and tomorrow, and tomorrow, harvest now, decrypt later, cyber attacks creep in this petty pace from day to day. And that's why, ladies and gentlemen, Albert Einstein described this as spooky. Thank you. Returning back now to the main thrust of the presentation, some scholars are skeptical of the likelihood of states developing cryptanalytically relevant quantum computers and the immediate risk posed by this data security threat. Although no quantum computer is presently equipped with enough qubits to execute Shor's algorithm for solving prime factors, that should not lull us into a state of complacency here in considering the full array of risks in this ecosystem. Why? Because acknowledging these risks earlier on helps states and industries come together in forms such as this to begin anticipating how do we establish the requirements for domestic and military entities to transition their vulnerable cryptographic systems to using more resilient, quantum-resistant cryptographic standards. In other words, why not prepare to lay that foundation today, to prepare for that worst case scenario, that tipping point, rather than during the actual crisis. So the time is now to begin this exercise of identifying what are our high value assets and prioritize them accordingly to protect them. Next slide, please. Here's where the Greek philosophy comes in. No human knows the future with certainty, and the wise Solon of Athens sagely pointed out to King Croesus at a lavish banquet centuries ago. Next slide, please. Thank you. Quote, "The future bears down upon each one of us with all the hazards of unknown, and we can only count a man happy when the gods have granted him good fortune to the end." Unquote. It is therefore an ambitious undertaking to propose a theory about how quantum technology will shape the future of warfare, especially given the fragile and nascent state of quantum systems that both myself and Professor Geraldine have described now. In that spirit, perhaps the saying "Festina Lente" should serve as our contemporary motto for championing responsible global quantum innovation. Festina Lente expresses the idea, make haste slowly, that doing something right the first time saves time. It was a popular motto of Roman Emperor Augustus Caesar, and this maxim also extends to the high-stakes geopolitical quest for quantum computing. And as states pursue quantum technologies, we must consider the legal and ethical considerations and the second and third order effects in this sphere. As quantum technology becomes universal, it will test the mettle of an international rules-based order in ways that we are not yet prepared for, such as post-quantum cryptography and more advanced autonomous weapon systems. The development and standardization and deployment of post-quantum cryptography is critical for minimizing these potential security risks to critical infrastructure and information and communications technologies. For all these reasons, I would argue that Festina Lente is a fitting North Star for decision makers to follow in convening multilateral fora such as this to discuss the risks as well as the fascinating opportunities around this emerging technology. With that, I yield my time to our moderator. Thank you.
Thank you very much, Chanda. What a brilliant presentation. And her presentation on the global cyber security concerns is really naturally liaised the second part of our discussion. But before that, I will now open the floor for questions. If you have any questions on the floor, please raise your hand. But I have already some questions on the chatting box, so please allow me to read some questions first. So I think these questions for Geraldine. I have a question about quantum coherence. What in real life it means, or does it terms of the advantages of quantum technologies?
Okay, thank you for the question. So, okay, let me say, I'm not sure the question, it's not only quantum coherence. Maybe it's, okay, in our real life, no, where do we have quantum? What does it change? It changes many things, but to give just an example that you may know, the laser pointers that we all use, in the 70s, a laser was just taking almost a big room like that one, no? And it's only with the development of nanoscale devices and the understanding of these materials and so on, that we are now able to have a green laser, blue laser, red laser, and so on. So the question was about quantum coherence in our real life, but in fact, it's really the three properties that I mentioned, energy quantization, quantum coherence, and quantum correlations, they enter already in our real world in many different technological devices.
Thank you very much. We can move on the second, maybe. So it is coming from my colleagues at the UNIDIR. Would it be possible to explain a bit more the slide on communication between two photons, one in Geneva and one in Lausanne? What kind of communication link can be placed between these two photons?
What was the end of the question?
So the end of the question, what kind of communication link can be placed between these two photons?
Okay, so in fact, you can have both types of, we call these channels, communication channels. One can have classical communication channels where you really send information. For instance, you share a key, and this is part of the protocol that my neighbor mentioned with the RSA, and you can also have a quantum communication channel where you will, which is based on a quantum protocol. And these two, I think what is important is that to develop secure communication, for instance, one application is quantum cryptography, and so you only there are protocols which were developed for quantum key distribution, which are, for instance, BB84, these are the names, or BB92. And these protocols, you have one part where you can communicate you can share classical information through the classical channel, but you have other things that goes through the quantum correlations, so through the quantum channel. So then I think it's very technical, but just to summarize, you can have both types of communication channel, classical and quantum, and then the protocols are there to develop a clever way how to use these two channels to improve security of exchanging information.
I could add a piece to that excellent answer with a case study. China successfully conducted the first ever intercontinental ground-to-satellite and satellite-to-ground quantum key distribution communication network between the quantum satellite Misius and a quantum communications ground station north of Hebei province in 2017. According to the system commander of Misius, this quantum communications network is, quote, the most secured method of communication because any eavesdropper will disrupt the entanglement and this activity would be detected. This test was also significant because it demonstrated quantum-enabled secure communications in outer space is possible. And according to NATO Review, one author in the NATO Review, he wrote that quantum key distribution could potentially be leveraged to enable ultra-secure data communications, potentially even make it completely unhackable, unquote, for military defense communication. So there's tremendous interest in this particular aspect of quantum key distribution, in addition to quantum sensing. Yes.
I agree. Indeed, also your remark now make me thinking that there is also another example which may be of interest for the people here. Now, is that, for instance, these quantum key distribution protocols are at the stage where some companies have been developing products, for instance, ID Quantique in Geneva. And locally, the state election in 2007, they were using these protocols for secure the elections. And in a geopolitics context, of course, this is also key to secure this kind of events and share the information.
Thank you very much. I vividly remember the 2017 Janna mentioned some news on the quantum communication in China was really quite impressive and shocking at that time in the community. So it is coming, I think, really accelerating the speed. Maybe here in the room, if you have any questions before I jump into the chatting, some questions. Okay, then I'll just move on to the. Oh,
Bonjour.
sure. Yes.
I'm Felipe Ribeiro from the Open Ethics for AI initiative. I would like to know how open source recommendations from UNESCO are being thought in quantum computing, and which are the best open source solutions in quantum computing nowadays. Thank you.
Maybe I can give you some time to think.
If I may ask, just to make sure I properly understand the question, thank you, sir. You are asking what are UNESCO's ethical recommendations for the use of quantum technologies? Thank you for the clarification.
What I can say from the academic point of view. So from the academic point of view, now there are clear rules to make all our data available. So as soon as you do some research, you write some codes, now it has to be available. And I think now it has really changed a lot in the last 5-10 years, and typically really everyone does it openly. Then what is the best open source? Now you have GitHub, you have several platforms where you can find the research and the code. Then as being part of the academic world, of course, there is a big gap between academic research and industry research, and some companies, only part of the code is available. Otherwise, they cannot make profit of their own development. So, for instance, some of the chips which are available for quantum computing by IBM or other companies, they are like some versions which are open, and which you can use. And this I don't know, but probably the code is not so complicated for this open version. But then the more advanced version with more technicalities, this one you have to pay, and I doubt they are open access. But this is only my small contribution to your question.
Indeed, it is a very thoughtful question, and I don't think my response here will give it justice, because it's a deeply philosophical one as well. But I will take this opportunity to highlight that an opportunity more locally here, close to home, here in Switzerland, that the government of Switzerland announced that in March, it will establish here in Geneva the Open Quantum Institute, and is working with 130 partners to explore developing an international governance framework and normative order doesn't directly tie to your question on open source in that regard. However, this is one example of disparate groups coming together, different stakeholders to talk about ethical concerns around this technology from many different aspects, from a systems thinking perspective. What are the moral, legal, and ethical, technological, economic, security considerations here? And I think that this effort by the government of Switzerland is an example, a positive example of the beauty of having more states come together to talk about this and share information about the threats posed by quantum systems to international stability and order. But you've raised a fascinating question. We could do a whole other panel on the open source debate. Thank you.
In more practical terms, you're saying that there is no open quantum framework in the market available for us yet.
If I can jump in, I'll present what the Open Quantum Institute is about, because it's an initiative by GESDA, which will indeed be launched in March at CERN, within CERN, which in itself has a very long tradition for open science. So we are working out the exact modalities. What I should say is it will be focused on quantum computing and the applications of quantum computing. But to build this initiative, we have, of course, been talking to a lot of the community, both from academia and private sector, but also philanthropy. And I can tell you that there are a few initiatives to boost open source, also in the development of the applications. I could, for example, I could name an initiative called the UNIDIR Fund that is looking at the applications and publishes as much as possible in the open. The result of those relatively small projects. There are some discussions about developing open source languages and also middleware and so on. But this technology is very, very new. So we are at the very beginning of even standardization in general. So deploying this in an open source framework is definitely at the center of a lot of conversations, but there is no agreed protocol or systems or framework so far. With the Open Quantum Institute, we hope that we can be part of this conversation because we have the multi-stakeholder platform, but we will be getting there slowly.
Thank you very much for the question, and thank you for the excellent answers. So I think we will close the first session of the dialogue, and we will have a 5-minute break, and then we will continue our conversation again in 5 minutes. Thank you very much.
didn't know really which level, at which level I should talk. That's really interesting. And I think, I think it's really important to not be afraid to think clearly and cleverly about new things. And it's not magic. So I think it's really someone tells you something is magic. It's not. And so that's why I think it's really and to be honest, being saying it's important to ask yourself techniques and are not discussions, but it's really important as people. That's fine, but we should reach a stage where we know it's good.
Thank you very much. We will resume the second part of our dialogue, and already we have many questions in the chatting box, and I will try to address those questions as much as possible in the second part of our discussion. And please let me introduce our third speaker, Mr. Gaurav Kirti. He is a head of advisory and emerging business and Ensign Info Security and an adjunct senior fellow at the Nanyang Technological University in Singapore. He has more than 25 years of working experience dealing with national security and policy issues. In the military, he served as a pilot, and his last position was the commander for Air Defense and Operations Command, while serving as a CIO of the Republic of Singapore Air Force. After the RSAF, he became the Deputy Chief Executive of the Cybersecurity Agency of Singapore, while acting as the Deputy Commissioner for Cybersecurity. He represented Singapore at the United Nations Open-Ended Working Group on Cybersecurity. Gaurav completed his undergraduate studies at Stanford University, holds a master's degree in public administration from the Harvard Kennedy School, where he graduated a distinguished Littauer fellow. The floor is yours.
Thank you very much, and thank you to UNIDIR as well as to Ms. Cho for inviting me here. I look forward to having a vibrant discussion with all of you later on. I cannot promise either props or Macbeth, but I will try my best to present a slightly more, perhaps diverse perspective on this conversation on two levels. I come from today the private sector, but I came in the past from the public sector as well as the government and the military. When I was in the government, I was in the National Quantum Steering Committee. Singapore is small, but we're very excited by the potential of quantum, and so we've got some research in that space already. But concurrently, I was also at the United Nations discussing the Open-Ended Working Group, where we discussed cybersecurity. And in that context, we discussed some of the risks of emerging technologies. Quantum came up quite often. Let me share 4 points, two kind of observations building on what both Jenna and Geraldine have shared before, but taking it a little bit further, perhaps. I want to caveat here first that even though my remarks may sound quite dreary, by nature, I'm an optimistic and positive person, but by work, we call it an opto-pessimist. I hope for the best, plan for the worst, and expect reality to look nothing like either of those. The 2 points, I'll start with the first point. I think both Geraldine and Jenna have shared that quantum computing will be extremely powerful in a way that we have not quite grappled with in today's classical computing. At one point, as she put it, when, not if, it will be able to decrypt the current encryption mechanisms that underpin the fundamental infrastructure of the internet. And let me be very clear, this is the fundamental infrastructure of the internet. Everything from the HTTPS to the way in which you send emails, to the way in which you communicate with each other, the way in which we trust each other online will be at risk. Maintaining secrecy online will become much harder. Establishing trust between two parties for transactions will become much harder. The risk that quantum computing will pose to this encryption mechanism will be significant. There is a lot of work on migrating to quantum-resistant algorithms, and ideally, hopefully at some point, post-quantum cryptography. But as we've seen in the last generations of transitions, transiting the entire internet from one baseline cryptographic standard to another cryptographic standard is a decade-long endeavor. And this was in the past when actually the internet was a much smaller place. Today, the internet is a much larger place. Transiting every single country, every single system, and every single form of trust, secrecy, and public key mechanism will take minimally that long. So we're going to see a decade of period where it's going to be a little bit tumultuous. So quantum computing will be very powerful, but that power may cause some instability in trust and secrecy online. The second point, and I think is worth bearing in mind, that quantum computing will not be like AI. It will be unequally distributed rather than equally accessible. Quantum is a physics problem. I think both the previous speakers have shared in great detail how complex that physics problem is. If I could liken it to a library versus an e-book, quantum computing will be like a library. It'll be books. But when I have a book, you can't read it. It will become physical properties that countries own and will be very difficult to share. E-books, on the other hand, all of us have it in our phones. All of us can access it on our tablets. Classical computing is easily accessible. All of us can have AI in the power, in our phones today. It will be a very long time before all of us have access to quantum computing, if at all, because the physics challenges are significant, and many countries will not have the resources, the technical, as well as financial capabilities to invest and build up their own quantum systems. As a result of this unequal distribution, it may even exacerbate some power dynamics. So as I mentioned, classical computing can be scaled through the cloud and through conventional chips, which deliver that power to your phone. We're very far away from seeing that same distribution mechanism for quantum. Those with access to quantum computing first will be able to have a disproportionate advantage over those who have access to quantum last. And this disproportionate advantage comes on many forms, whether it's the access to the potential of quantum to do great things for the world, or the access to quantum to decrypt data that is sensitive for the rest. I think we also need to recognize that there is a timeline issue here. Today's data that is encrypted with conventional cryptographic methods, as mentioned earlier, the harvest now decrypt later type of attacks will be vulnerable. There is a potential, and I think we're very excited for the, let me get this term correct, ultimate security. We are all very excited for ultimate security to come about through quantum computing. But let me be very clear, ultimate security will only benefit those who have access to quantum computing in their home country. It will be very difficult for smaller countries, less well-off countries, to have access to ultimate security. And as a result, they may find themselves in a position of ultimate insecurity. What are the geopolitical implications of smaller, less well-off countries not being able to secure their information with the same level that bigger, more well-resourced countries have? Two kind of comments about what we can do about this. The first one is a very practical one. I think we've already spoken about how sensitive information needs to be encrypted using quantum-resistant algorithms and eventually post-quantum cryptography. That's the small step. But the transition will take many years, perhaps even decades. And I think one thing we need to discuss and have more conversations on is how to have these multi-stakeholder conversations about governance and controls. In the cybersecurity world, we have the open-ended working group where we discuss the norms of responsible behavior on the internet. What should states do and not do when it comes to behaving themselves on the internet? We need a similar conversation for quantum. I would say that one of the biggest risks we need to think about is what happens when quantum computing becomes militarized. And again, because quantum computing requires a heavy resource investment of talent and money, it tends to lend itself very well to large defense programs that have those talents and money. If militarized, unfortunately, it may lead to a new type of arms race in the development of more advanced cyber or autonomous weapons. How do we manage those risks? I propose that we consider defining global norms of responsible use of quantum technologies in general, and whether the way in which these powerful technologies are used by the few who have access to them is subject to some level of scrutiny. This is not a new concept. We have also seen other types of very significantly powerful systems, technologies, that have a disproportionately dire impact on the world, being subject to scrutiny by international agencies that come down and inspect how that technology is being used, whether it's being used for power or weapons. And I'm obviously here referring to IAEA. Do we need to have the same level of scrutiny on the use of quantum computing and how countries are using quantum computing? It's an open question. But I want to caveat that governance of emerging technologies is extremely difficult. I think in an ideal world, I would love to make haste slowly, but we have shown repeatedly as a digital domain that we prefer to move fast and break things. The events surrounding OpenAI in the last few weeks are illuminating. There's a board of governors who are responsible and entrusted with governance of the direction of AI. There was a CEO, there were investors, there were shareholders and stakeholders. And all of those interests at some point came to a slightly divergent perspective, which resulted in what we saw unfolding. But the point is not OpenAI specifically. The point is that the trade-off between profit, the trade-off between the power and potential of these emerging technologies, and the need to move more cautiously and slowly when it comes to such a powerful and possibly dangerous technology is difficult to manage. We will see this with AI, and we will see it again with quantum. Every country has placed its own flag somewhere there that by 2020X, my country will have a quantum computer. That is not a conversation about making haste slowly. That is a conversation about making haste. How do we intervene to make the governance conversation part of that track? And I think, again, to reiterate, a multi-stakeholder approach must be the way that we bring these conversations to a fold. It needs to involve the academia, the public, the private, and possibly even the military sector, because these conversations require platforms like UNIDIR and platforms where multi-stakeholders come together and discuss the risks of these emerging technologies. Thank you.
Thank you very much. It was really, there are many of the food for thought, maybe ultimate security versus ultimate insecurity, disproportionate advantage or disadvantage. And I really hope we can pick up some of the really key words during our conversation later on. And our next panelist is Ms. Emily Violi Benjamin. She's the program manager for the legal and policy team supporting Microsoft's quantum program. She is responsible for Microsoft initiatives on quantum policy, ethics, and governance, as well as government and civil society engagement. Before joining Microsoft, she supported cybersecurity strategy and communications at Palo Alto Networks and Sony Corporation. She is a graduate of American University BA Economics and International Relations and the University of Maryland Cybersecurity Policy. Emily, over to you.
Great. Thank you so much. And thank you to UNIDIR for having me. I think this discussion is not only incredibly timely given where we are at in the critical development of quantum technologies, but it's also very important to our continued understanding of how these technologies are going to develop. What is the timeline? How are they going to be applied? And what is the impact that these technologies will have on peace and security? I think just to get started, the previous speakers did such a fantastic job at explaining, what quantum technologies are, why are they unique? But I think it's helpful to point to a couple of points on, how we understand that quantum technologies will be used and applied in our economies, specifically quantum computing, and where are we currently, so we have an understanding of what the timeline is and how we need to respond. So first on impact. For quantum computing specifically, the most promising application is in chemistry and material science. Specifically, quantum computers will be excellent at simulating quantum systems. And this may seem like a very narrow application for computing, right? Chemistry and material science, advancing computational chemistry. But 96% of manufactured goods globally are underpinned in chemistry and material science. And when we think about the Sustainable Development Goals and the challenges that as a globe we need to come together on over the next several years, fundamental chemistry and material science problems underpin nearly all of them. So the application of quantum computing in this space is enormous and has significant potential for not just economic good, but societal good. On the timeline, in order to reach this potential for societal and economic good and solve these chemistry and material science problems, we need to have sufficient compute power to be able to do it. Right now, today's NISQ machines, these noisy intermediate scale quantum machines that are very helpful for R&D and academic purposes, do not present practical quantum advantage in that they cannot solve these large intractable problems that are intractable on classical computers, but will be able to be solvable on quantum computers. We will need a quantum supercomputer for that, and we are not there yet. So on to the impact on peace and security, and first to the risks. The first and perhaps the most established and most talked about in this forum was the risk presented to cybersecurity, specifically the risk presented to public key asymmetric encryption. We've talked about this at length, so I'm not going to go into many details, but one thing to note here is that there is a path forward. We must migrate to post-quantum cryptography quickly where applicable. We need to adopt symmetric key cryptography where appropriate, and we need to do this with urgency. While the timeline to a quantum supercomputer, so a quantum computer that would be able to solve these large, intractable computing problems, we know we need 1 million or more qubits. We are quite far from that. The timeline is still long. We cannot wait to migrate to post-quantum cryptography, and we have to do it with urgency. The second area of risk that I would like to touch on goes back to chemistry and material science. And it is actually not unique to quantum computing, but it becomes very acute when we think about the risks associated with quantum computing, given the compute power behind quantum. And that is the dual-use nature of quantum computing, and specifically advanced computing applied to chemistry and material science. Chemistry and material science R&D is inherently dual-use in that the computing tools that we could use for good can also be used by a malicious actor to create harmful chemicals. Given that quantum computing will enable us to do computational chemistry with increased accuracy, that AI will allow us to generate new chemistry and new molecules faster than ever before, the potential for this, not only in our economies and our societies, is truly transformative, but we have to be very mindful of the dual use risks here and come up together as a group with a multilateral governance framework in order to manage these dual use risks as we move forward with this technology. Again, this is not a risk that is unique to quantum, but something that is imperative to the discussion of governance for quantum computing moving forward. And then the third area of risk, which was also touched on a little bit earlier, and is not actually also unique to quantum capabilities, but rather the ecosystem at large. And that is the risk that this technology will be developed and adopted by just a few countries and narrowly held. And the risk that the impact of quantum computing will be narrow rather than this broader societal impact that we know we can derive from its applications in chemistry and material science. So how do we get to a point where we can meaningfully adopt quantum technologies while mitigating the three risks I listed above? First, we cannot wait to address these risks until a quantum supercomputer arrives. We must act now. Second, we can't operate in silos. We can't operate in silos geographically, and we can't operate in silos across industry, across international organizations and government and academic institutions. We must work together. And I think there are three priorities that can guide us as we think about the road to this broadly adopted, societally impactful quantum ecosystem. The first is that we must work globally to ensure that quantum technology benefits all of humanity and not just a privileged few. How do we think about doing this? We must build quantum use cases and applications that are working to drive scientific discovery and can condense hundreds of years worth of scientific research that we know that we need into just a few decades. These tools, these applications with the quantum compute power underneath them will allow us to address some of our generation's gravest challenges. And that includes making progress against the climate crisis, leveraging quantum computing, in making progress against food insecurity, leveraging the quantum simulation capabilities that quantum would enable, and making progress against new treatments for existing and novel diseases. Finally, we have to focus on developing a quantum supercomputer, meaning that we need a quantum computer that is capable of solving these challenges for us, and we have to drive towards that goal. Second, we need to think about how we can protect against malicious use of quantum computing and develop meaningful controls and governance to ensure that quantum computing and the applications it enables is used responsibly. First, as I previously mentioned, we must accelerate the migration to post-quantum cryptography and quantum-safe technologies. This is not just because the threat exists today with the harvest now, decrypt later scheme, but also because, as was previously mentioned, this will be a long road and will take a lot of time to do this. We have to start now. We also have to coordinate across industry, government, and civil society to develop a responsible computing framework that can be applied to quantum computing and will address dual-use risk in chemistry and material science. This includes potentially exploring adopting product-based and user-based controls alongside industry leaders to prevent malicious actors from gaining access to future quantum and advanced classical computing abilities. Finally, we need to think how we can democratize access to the quantum economy through skilling and workforce development and through building up our global digital infrastructure. This includes creating new programs and leveraging across all of our industries and all of our groups to develop new skilling and education programs that not only aim to build the workforce that will help develop these technologies, but will adopt and apply them. We need to think about how we can cultivate more public and private partnerships to expand the societal impact of quantum computing and ensures that it reaches the communities that are most in need. And we have to think about also how we can further develop the underlying infrastructure that we will need for quantum computing. This includes access to the cloud, broadband, 5G, and additional advanced telecommunications networks that we will need to fully adopt quantum. As we've learned with AI, we cannot wait until the opportunities and the risks are right before us to address them. We've learned that the technological landscape can evolve very quickly, and we have to think about now how we can put meaningful governance frameworks in place to ensure the responsible use of quantum computing and the application it enables in the future. And forums like these in this discussion are how we will begin to develop a collective response to these risks, how we can partner together to ensure the responsible use of quantum computing in the future, and ensure that the impact of quantum computing reaches all of humanity and is able to target some of these broader societal challenges that we have. Thank you.
Thank you very much, Emily, for highlighting some of the societal impact, dual-use risks, multilateral approach, public-private partnership, a proper infrastructure, and urgency of the discussion among multi-stakeholder like today. And I think we have much to discuss further in our later discussion. So let me introduce our last, but certainly not least, panelist is Ms. Andrea Rodriguez. She's lead digital policy analyst for the EU Digital Agenda at the European Policy Center, or EPC, a Brussels-based think tank, and the founder of Policy Pulse, a deep tech consultancy. She has published extensively about the intersection between quantum technologies, cybersecurity, and security, and has been part of several advisory groups, including at NATO. Andrea teaches regularly about the EU digital agenda and strategic technologies at different European universities. Andrea, the floor is yours.
Thank you very much. It's always a hard task to be the last speaker, especially when you're preceded by brilliant minds who definitely have touched on some of the topics that I wanted to speak about here today. So if you can go 2 slides, not 1, 2. So I had 1 slide about the benefits, and I have 1 about dual use. So if you would allow me, I would like to try to tackle a little bit both aspects in this slide. So as we have seen, or I think that it has been said in this panel, quantum technologies have a real transformative, transformative impact, and that's helping on the one hand the emergence of a new type of economy, and therefore we're having more and more applications that are market ready, and that's creating new dynamics, and on the other hand they're also posing new challenges for international security. So in this slide I wanted to speak about the dual use of it. It's great that we are seeing how quantum simulation is the simulation of quantum dynamics is helping us for drug design, but nonetheless, if you just click on the next one, I was supposed to do this, but unfortunately interoperability is a thing. It can definitely also help us the design of new biological weapons. Indeed, quantum sensors can help us it can have vast applications for better healthcare, as well as this geosurvey. Imagine that you're in search of new materials, of raw critical materials, which is one of the things that, at least from the EU side, it's something that the EU is extremely worried upon. But how about you also use this for next slide, for locating assets in a battlefield scenario? you will be able potentially to locate, for instance, like underground bunkers, precisely because of quantum mechanics, as it was explained in the very beginning. Better atomic clocks can be super interesting right now, that we are like having like more and more digital assets being used together. Like, for example, in the case of smart cities, like to synchronize transportation flows, to like smart like the energy grid, but nonetheless, it's also going to be like really helpful in the military context for like better, as I'm saying here, like operational readiness. Of course, quantum navigation devices are definitely going to be really useful for the creation of new applications, but nonetheless, it's also like going to help the military to have like to be independent from space systems using the quantum compounds, for instance. Ultra secure communications using quantum links, which is one of the things that has been mentioned before, is also going to be really useful. But nonetheless, it's also going to help us create or enhance something that has been said before, which is the cybersecurity dilemma, which is, I come from cybersecurity. That's one of the things that I have been working on a lot. And there is like this scholar, Ben Buchanan, who already in 2016 said that states spy each other, and therefore that contributes to international peace, because we all know everybody does it. And it really helps clarify some of the uncertainties. What if what if we move to the future, and then like we're able to create like quantum networks, and part of this information that also help us like know what our geopolitical adversaries are doing will be moved into like extremely opaque systems, in which is going to be really complicated to spy. What's the impact in uncertainty, in the race of uncertainty, so therefore in the cybersecurity dilemma? That's another question that we have. And quantum computers, of course, this is something that has been said before. It's going to be, it's a foundational technology that is going to allow us to do like most of the things, or a lot of things said in this slide, but definitely it poses a big challenge, which is like breaking current encryption systems. So next slide, please. I was going to focus on this too, but I'm going to try to just like go a little bit real quick. Next slide, please. So this is a small table that we did at the European Policy Center. We published a paper in July when we were like trying to advise the new European Commission to adopt a quantum cybersecurity agenda. The paper, you have like down there the reference, but I thought that it could be useful to bring to this fora this table today, because I think that it translates technical things like certain standards into examples of today's use. So as one of my previous co-panelists said before, everything right now, it's everything digital right now is encrypted, and because we are increasingly basing our societal interactions, economic interactions, political interactions on digital networks. Therefore, if there is like this challenge to break encryption, where is it going to hit? And as you can see here in some examples, it definitely potentially will the impact will be everywhere, from the internet traffic to VPNs to financial transactions, e-passports, which is to me one of the most interesting things. How about digital products that are deployed and they're supposed to have a long lifetime? What is it going to happen when all of a sudden in 5 years, 6 years, we can have significant disruption? Well, how are we preparing for that? That's another big question that we're having. So next slide, please. No. So all in all, what I want to say is that challenges have an all-over effect. So this is not only a question of cybersecurity. It isn't only a question of dual use. How about societal implications of this? At least I come from Brussels, so most of the work that I'm doing, of course, applies to the European Union and European societies, and there's like several trends that we have seen emerging over the past few years. One of them is political polarization. Another one is like enhanced public distrust on public institutions, and therefore, if you have effects such as the ones that I'm just putting here as a matter of examples, how is it going to affect? Well, certainly it's going to be food for hybrid attacks. So I think that's another thing that we definitely need to think about. At the European Union, for instance, it was promised that the EU will release a hybrid toolbox, and I think that one of the reasons it hasn't come out yet is because it's as technology advances, so the implications on hybrid. So I have here some examples Some of them have been mentioned before, such as attacks on critical infrastructure, national security crisis being more often, intelligence leaks, which is something that it's particularly worrisome, at least from the EU perspective. More or less every member state, more or less, have national security, like national intelligence laws that provide some timelines of when do like certain type of intelligence, like when does it have to be released for the general public. And that normally is a 20, 30 or 50-year window. On average, let's say it's like 25 to 30. We, at least if you look at the academic research from 2026 to 2030 on to 2035, that's when right now the foresight is that the disruption will start to be felt. That's a maximum 12 years time, meaning that if we have like an average of 30, we are 18 years late. So how does that impact on public trust? IP theft from the company perspective, definitely that's going to be a big concern. Loss of competitive edge if you don't have access to the technology, to these technologies, and you cannot develop cutting-edge applications. How is it going to impact, for example, in the EU side, European competitiveness on the medium and long term, data leaks being more often, and better info ops. So next slide, please. This is an example of what has been done in the EU at the moment, and I chose this, the Greek, for one reason. It has been said before that when it comes to securing information, I have like two avenues. The first one is it's more on the classical realm of things, which is the transition to post-quantum cryptography, which are mathematical algorithms. They're not based on quantum mechanics. They're not based in quantum physics, but they are believed to be quantum resistant. Because they solve like some of the issues that right now we have, such as like having or relying on security, for example, on factorization. But then there is the other way, which is like through the creation of quantum channels and quantum links, which has been explained before. And right now we're seeing that if you speak to the different communities, if you speak to different countries, it's really difficult to see like a common perspective in this, which one to use. One of them promises a breakable security in the long term. Another one is more of a short-term like fix, how both solutions can cohabitate. The Greek example to me is a very interesting one. So, for example, from the part of like quantum communications, one of the things that we are seeing is that there is a strong authentication problem, which potentially can be problematic. Here, this is a map of Greece with like different like links. Like as you can see, they are like thinking of they're like implementing quantum channels, which is the green lines, and then like of course to create like long distance communications, they're using satellites. But the interesting things is that they're like trying to use both technologies together, post quantum cryptography and quantum key distribution, to try to enhance security. I wanted to bring this up because if you're interested in the topic, to me, this is an interesting thing to monitor. So next slide, please. So because of that, and because of the things that have been mentioned before, and so do the rest of the panelists here today, it has definitely created a race for quantum supremacy, which is to control, which to me is a keyword, the access, which is the second keyword, like quantum technologies, especially at the computing level. I think that the race is mostly for quantum computing, and at the EPC we have been working several years on this topic. So we have been monitoring the ecosystem, as you will see, because I will offer you two tables. We have selected some non-EU countries, and then this part of the table plus the next table is all EU countries, and you will see a lot of blank spots, which I think to me is a very interesting thing. As you can see, outside of the EU, several countries have jumped on the quantum race, if we want to say it this way. Some countries have already like put in place national strategies. Some of them have strategic funding programs, which is dedicated pots of money that they direct to develop quantum technologies. And some of them, they have quantum programs, though they do not have a national quantum strategy. The difference between a quantum program and a national strategy for me is who does the oversight and the monitoring, doing, and B, what are the objectives. Countries that have a national quantum strategy tend to think more about the dual use implications and about the implications for national security, whereas like those who have a quantum program, it's more like focused on the development from the scientific perspective of certain like KPIs. So that's on the non-EU country side. When we go to the EU, for instance, the EU has 27 member states after Brexit. Only 4 have national quantum strategies. 4 of 27, it's a lot. 6 have quantum programs, but increasingly we are seeing the more strategic funding being put on the table, especially after 2021. The global pandemic was a big hit for absolutely everybody, but in the EU also had strong geopolitical implications, and that's one of the reasons why after 2021 the European Commission decided to create something called the Next Generation Funds. Maybe you're familiar with it. A lot of money for the recovery and resilience of European economies, and one of the targets was you need to dedicate this money 20% for digital transformation projects, and a lot of countries decided to jump into quantum because of that, because all of a sudden you had to dedicate it, and it's like, okay, we're seeing that potentially this is going to be interesting for us. We're going to go and jump on this, but increasingly we are seeing this initial thought of we do not want to lose our scientific edge into this is going to have real implications for our national security. So strategic funding is being converted into quantum programs and turning into national strategies. So that's another thing that you will see in the next slide. It was mentioned before by one of my co-panelists that the European Commission has given funding for the creation of 6 hybrid supercomputing, like classical supercomputing and quantum programs, and then you can see it actually on the table. So those that say Euro HPC-Q were like one of were a winner of this competition. So indeed, we have like several of them. As you can see, also I have also like put some countries that have national strategies or quantum programs being like thought of or in process or in progress. They have been announced but yet not released. So I would like ask you to keep an eye on this. So next slide, please. So these are my conclusions, and unfortunately my conclusions are questions, so I'm not sure to what extent this is actually a conclusion, but I think that many things have been said like here, and I think that speaking at UNIDIR is not the same as speaking at the European Commission, and I think that really allowed me to reflect on other issues, such as one, if what I mentioned is like great, like economic impact and national security impact, how about like equitable access to the benefits of quantum applications while reducing risks? How about when all of a sudden like the countries from the tables like have access to these technologies, and therefore they can secure the systems, create like applications and new materials and all, and then that is going to help for the reshuffle of the global economy. How about like less privileged countries, if I want to say it this way, those who as of now do not have either the access nor the opportunities to partner with countries, because this is obviously also impacting open science and international scientific collaboration. What can we do like in that respect? How about securitization? As I mentioned before, strategic funding programs are becoming quantum programs, are becoming national quantum security programs, which is like obviously a sign of the times that as technology advances, the potential for disruptive applications are being seen, and therefore more countries are jumping into the race, which is also creating great tension at the international level. So how can humanity collaborate to solve common challenges? Food security has been mentioned before. Climate change certainly is going to be, or is already a big issue, and we have seen that quantum computing as a foundational technology is going to definitely help create new algorithms that could be like really interesting for simulations as well, and to like create new solutions. How about using the capacity to create new drugs to improve global health, which I think is another thing that it's definitely of big concern. And then perhaps like 2 more provocative questions for today's panel. Does it even make sense to speak about promoting responsible development when we're seeing that the landscape is being increasingly fragmented and then securitization is becoming increasingly important? Or even quantum ethics. I'm referring here, for example, the World Economic Forum released last year or 2 years ago, like the responsible development for quantum technologies principles. Some of them were very interesting to me, such as accountability, like non-misuse, and so on and so forth. To what extent these are actionable and really like able to be put in place. Is it time for quantum international norms? As a cybersecurity person, that's something that I have mixed feelings about because of how useful they're been. But we can see that increasingly when you bring this conversation to international fora like this one, really interesting things happen. So those are my 4 concluding questions for you as well. So thank you very much.
Thank you very much, Andrea. And I'm really glad you brought up some region perspective, EU perspective. And then I think when it comes to the discussion on emerging tech and its implications, I think we need more and more regional perspective as well as the socio-technical perspective while we pursue some multi-stakeholder dialogue like today. So with that, I would like to open the floor for questions. And we have already some questions in the chatting box, but yes.
Thank you very much for your very informative and interesting panel discussion. I'm a student at the Graduate Institute, and I want to take a step further to ask and curious to know your thoughts on the role of quantum technology and quantum computing for future peace building, because the innovation of digital peace building has been mentioned in academia as a way to decolonize peace building or to rethink this peace building. And I'm curious that, in your opinions, what can the quantum technology bring to the table, adding to the existing peace building agenda? Will it has like positive impact on peace building, or it will actually bring a negative impact on peace building operation? Thank you.
Yeah, I can, make just kind of a couple of comments. I think, when we think about how quantum technologies have the potential to be applied for positive societal impact and creating greater security in societies through food security, climate security. I think that quantum technologies offer a lot of benefits, not just even computing, but there are even applications in sensing and the way sensing and communication networks quantum communication networks can be implemented to promote more secure societies. And so, there are many scientific examples that I think we could point to there, and a lot of opportunity. To your question on whether or not it could make society less or make peace less likely, I think it goes back to ensuring that we are putting these technologies to use for problems that impact all of humanity, and that we're building equitable access to the benefits of quantum computing and what it will allow for, rather than keeping them from countries that have traditionally not been included in these technological development cycles and the adoption of said technologies. So I think there's a balance. We have to be operating on multiple fronts in order to push this forward.
Thank you so much for the excellent answer and question. I think in the end, the peace building activities consist of all societal impact, and that we are now at the moment to think about the more broader societal impact which quantum technology could bring about. And then in the end, as Emily mentioned, some of the access and disproportionate advantage, how we can kind of contribute to more proportional advantage the quantum technologies can bring about around the globe. I think that could be the first question when it comes to the peace building activities using quantum technologies in the later phase of our discussion.
Could I just add a reflection from how we've had this conversation at UNODA? So disarmament affairs, and applying a disarmament lens to the same conversation. No, it's not quite the same, but it might be useful. A large part of the conversation there is really about accountability. How do we create mechanisms for accountability of the use of this new technology? Trust comes from knowing that to some extent, we all have to follow the same rules, and there is some level of scrutiny as to whether or not we're following the same rules. Cyber has obviously made it much harder to make sure that people are following the rules. But in more traditional kinetic weapons, we've had those conversations about accountability and scrutiny. The other two parameters which we may want to think about for peace building is interdependence and access. In a technological ecosystem, which is a competitive one, where I want to build the entire value chain internal to myself, actually that becomes less interdependent and becomes therefore more of a national security, national capability, nationalized capability. In technologies which are interdependent, I will build one part, but I require your part and your part and your part to all come together for it to work as one system. There is inherently more trust. So things like OQI, I think, are in the right direction, where you are inherently building a system that requires multiple parties to come together by design. But the challenge is we have to manage the tension where countries want to make sure that the whole stack is their own. And I think that is the tension we have to look at. Thanks.
Thank you very much. Yes.
Thank you. My name is Sammy. I'm from Canada. I work for government nonprofits, and we try to promote quantum adoption and quantum awareness. My question, maybe we spoke about unequal distribution of technology. My understanding is that for post-quantum cryptography or for any measure of cybersecurity, we don't require a quantum computer to generate those algorithms. So do you think that will be a less uneven distribution, given that it's not dependent on the race towards the quantum computer? And if not, what can be done? I mean, it's maybe a difficult question, but is there anything that can be done to help a more even distribution of cybersecurity or protection against quantum computer? To anyone who would like to take it.
PQC, and I think I'll leave it to the other panelists. Post-quantum cryptography is going to be available to everybody, but I think the challenge is that post-quantum cryptography has taken a really long time to get right. One of the awkward dilemmas is that post-quantum cryptography is great against quantum computers and not so great against classical computers. You can't have your cake and eat it too. And as a result, even the whole shift of migrating everything to PQC, people have shown that very low-powered computational attacks can break PQC. And that's why it's taken NIST so long. And it's not that they are not working hard on it. PQC is unfortunately not the panacea. It will solve one set of problems, but create another set of problems. And having an algorithm which is resistant to both classical as well as quantum attacks is proving to be much harder than we thought. But the good news is that it's accessible to everybody. But that is a classical solution to, I would say, delay the problem, not to solve the problem.
And just to add quickly on the global access, we've spoken just a little bit about the NIST standards. I think what's been helpful in looking at the NIST standard and the adoption of these potential adoption of these protocols globally is that there's a lot of collective global action on this and recognition and kind of rallying around ensuring that we have harmonization in this process. And so I think that has been a great example of how we can kind of adopt and address these risks more with a global mindset rather than leading to fragmentation of standards and greater confusion across the ecosystem.
Thank you very much. And
thank you so much. Marisela with JESDA and a diplomat in my previous life, and kudos to UNIDIR for this excellent panel and to the excellent presentations, of course. I was just wondering, because I see a lot of commonalities in the way you are approaching the need to democratize, socialize, include more voices and sectors in this conversation around quantum computing, its impact, its potential benefits, but also risk. And coming from an underrepresented region, from Latin America, I wonder, how can we include also other regions in this conversation, raise awareness, and make sure that this broader discussion around, building implicit inequalities in the way that technology is develop can be addressed, because I think that this is a very important point, and I wish that more people, more countries, more sectors can engage in this important conversation. Thank you.
I can take that. JESDA is such an important partner to Microsoft on these issues, so it's great to all be here together. I think there are a couple areas that are really ripe for partnership in regions that are either have been underrepresented in previous technological developments or that are not currently represented in quantum. But I think one point that you made, and I think others have made, is that it is really impactful that we're having these conversations so early in the development life cycle of these technologies, that we are learning from previous technologies and able to try to get ahead of some of these concerns very early on. So I think that's fantastic. I think one area where we can work together globally and, work in nations that have really traditionally been represented as these kind of leaders in technological development and bring other regions with us is the development of quantum applications, right? The work that the Open Quantum Institute is doing to develop applications and algorithms around the Sustainable Development Goals. I think another area is, workforce development and skilling, building these private-public partnership and alliances across countries to ensure that we are building a workforce that not only is, importantly, leading to the development of quantum technologies, but even more importantly from an economic and societal impact is we need more chemists. We need more computational chemists. We need more people who will be adopting these technologies in their work. And that is a really, I think, fantastic area for global partnership and bringing other regions along with us to reap the benefits of these technologies.
Adding to, yes.
Like maybe if I may for a second, I think this is like diplomacy will have to play an important role in here. Because otherwise, I think this is something that is not unique to quantum. It's something that we have been seeing over the past 5 to 10 years, which is like global fragmentation in technology influence spheres. And I think that this is something that when it comes to of course like quantum technology is like really important. And then I think that the part of the reasons why we're having these conversations so early on is because we still have this legacy from the conversations around AI that is still ongoing. So I think that diplomacy is going to play like a really big important role. For instance, I know that some EU member states have bilateral agreements with a lot of like non-European countries also to co-develop certain quantum applications, and I think that I would definitely say that right now is the role of regional organizations to really be outspoken about these issues as well. I'm Spanish, so I know very much of like bilateral relationships between like Mercosur and Spain and how like that is also impacting at the conversation at the EU levels. But I would only like see that first we need to raise awareness between like diplomats that this is something that is going to impact short-term, mid-term, and definitely long-term prosperity of the regions. And second, like bringing this up to like the higher conversations. Otherwise, we're gonna see this trend like probably like being more like more grave over the next few years.
Thank you very much. I just wanted to mention, adding to our colleagues' comments. So from UNIDIR's perspective, it's really, really important to have you here and online as well, because you will play a really great role to bridge from some of the discussions here in Geneva and your home country. And I think I really value that presence, your presence today here in this room and also online, to start this discussion on not only quantum but also emerging technology in general. So I really, really pleased to have this esteemed speakers as well as the esteemed participants today. I just wanted to mention that before we just move on to the next question. We have many questions in the chatting. If I may read one. Let's see. So I think this question is quite related to and relevant to our the comments. Whose role is it to develop international norms if we are being realistic? A diplomat told me we'll never be able to develop rules for a techno that's not developed yet. When we already struggle creating norms for technology that's out there with parallel with the space. While a quantum startup told me it's not his role, is it the role of governments? So I think we could understand the essence of the question.
So maybe I will put on the hat of the former deputy commissioner, so a government hat for this particular answer. whose role is it to govern? The government. It's in their name. And governance comes in the form of implementing rules, laws, legislation, regulatory frameworks, all of the tools that governments have. Is it easy? The answer is no. But is it their role? The answer is yes. 2 points to illustrate what this means in the IT context. And I will respectfully disagree that we have not done it for other domains. I think for space, we have Artemis. For the open-ended working group on cybersecurity, I will agree that it's been a difficult process, but we do have norms of responsible behavior. Again, whether or not we can impose them, whether we can implement them and execute them, those are important, but second questions. We have come together as global community to define what those norms look like. I think the specific question on how governments can implement legislation is one that I'll use a specific case study from Singapore. IoT, Internet of Things devices, became a huge challenge to big and small systems alike. Botnet attacks was a particular concern of ours. And so in Singapore, we decided that even though we're a small country, we will create our own standards, we'll create our own framework, and we'll create our own governance around IoT devices. That standard basically came in the form of a labeling scheme. And basically the idea was that we would require all devices to put a nutrition sticker on the side of their box. 1, 2, 3, or 4 star, or 0 star. If you choose not to participate in our scheme, we will give you a free 0 star, and then consumers can make up their own mind whether they're going to pay for your 0 star device or pay for the guys who are 1 star, 2 star, 3 star, and 4 star. So we've been doing this for about 2 years now. The White House just announced that they're going to do the same thing, and we've been sharing data with them over the past 2 years. The point is that it is not easy to design governance for emerging technologies, but it is necessary. I think the latest announcement on the responsible or the design of AI to be secure is an important step forward, but a lot more needs to be done to translate that into the language of laws, into the language of liabilities, into the language of regulations. A specific second example, and I'll end after this, is when Singapore first implemented the Cybersecurity Act, and this was around 2017, we took a criminal negligence perspective to the failure of critical information infrastructure systems. Meaning, if you are building a digital backbone for a hospital and you did not secure it properly and it goes down and people die, it is the same thing as you built a building without a fire exit. And if people die, it was your fault and you go to jail. So we had jail term in our legislation for the Cybersecurity Act. Obviously, in 2017, when we put this out there, it received widespread comments. But today it's a well-functioning system for us. People who build digital systems that support electricity, that support trains, that support hospitals, design it securely because they know that they have a responsibility to do so under the law. It's not just a good to have, it's not just a recommendation or a guideline. We will put you in jail if somebody dies because you did not secure your system properly. Thanks.
Thank you very much. I think it's time to close our dialogue. But before we close the session, I'm really pleased to have Ms. Marike Hu, Executive Director, Impact Translator, Geneva Science and Diplomacy Anticipator, GESTA, to offer some closing remarks. And please allow me to introduce her. Ms. Hu holds a master's degree in management from Amblin Business School and a master's degree in urban planning and development from University of Paris, Sorbonne. She began her career in strategic consulting, where she advised local, regional, and national governments on economic and innovations policy. And she, in August 2020, she joined the GESTA, where she has operations, private sector innovations, and public affairs. Right, you have that.
Thank you very much to UNIDIR for the invitation. I'll just start by those closing remarks by offering 3 key takeaways of today's discussion. First, on the technology aspect, what I wanted to stress here is that when we speak about quantum technologies, actually we speak of a multifaceted reality. So we're speaking about all of those technologies, of course, are leveraging the properties of quantum physics, but we are speaking of very different things when we talk about quantum sensing, quantum communication, or quantum computing. And even if we take just quantum computing, the different technical modalities to leverage those quantum properties to build a quantum computer can differ quite widely. So again, a multifaceted reality and those technologies are at different stages of maturity. So the question of timeline is indeed very important when we speak about governance. For quantum computing, which is the focus of the work of GESDA, we see that the issue is to scale what is being achieved in the labs, in the academic labs, but also in the labs of industry, to make quantum computers, to build quantum computers that are actually useful in real life to solve real life problems. And that may take around 8 to 10 years. And for those computers to make an impact, they first need to exist. And that would need academia, industry, and private sector research to work together to achieve those promises. So that was my first takeaway. Second takeaway is about security. We learned today that once those quantum computers are at scale, then our current cryptographic schemes will be broken. We also learned that we have technological responses in the form of QKD and in the form of algorithms. Some of them are approved by NIST in the US. So we have technological responses to that. And what we have to do now is to make sure that those technological responses are rolled out fast. And that is also a question of governance, which is the focus of today's dialogue. My third takeaway is about societal impact, and that's the core of the work of GESDA. So what are we going to do with those quantum computers apart from breaking current cryptographic schemes? And there we learned that chemistry and material sciences applications are where the quantum computing community is most agreeing that the potential will be. There's some debate about the quantum advantage on optimization, machine learning, and so on, but more or less everybody agrees that there will be significant advantage to develop new materials, new chemistry applications. But that's not the end of the problem. The end of the challenge is for us to find what those chemistry and material sciences will be used for. So how can we leverage those chemistry and material applications to help enhance food security globally, address challenges in public health or climate change, for example. And that should be the case for all. So equitable access to the computers is also important for all those who are affected by those challenges to be able to leverage this new technology to solve or help solve those challenges. And I hope that what we're proposing with the Open Quantum Institute, so it's an initiative that is a first science diplomacy-based initiative. It's important to know. It was curated by GESDA for the past 3 years as a multi-stakeholder global initiative that will be hosted at CERN, starting from March 2024. We hope that with the Open Quantum Institute, we're providing a response to the key takeaways that I mentioned earlier. So the Open Quantum Institute's aim is to provide a safe place for quantum computing to be leveraged to tackle humanity's greatest challenges. That's the first key goal. The second key goal, and they're closely interrelated, is to mitigate the risk of creating a new digital divide. And that is very important, this inclusivity in the development of the technology, but also in leveraging the potential for the applications. We feel that all of this will only be possible if we activate multilateral governance. And of course, there's a question that was clearly stated earlier about how we can ensure that we have the right human capital to activate the potential. So here I will now, if you don't mind, we will show a short video that is presenting what the Open Quantum Institute is about. We can move on to the next slide, which actually I will just give you a bit of an overview of what those 4 A's actually mean in practice. So this initiative was, as mentioned earlier, developed as a multi-stakeholder initiative. So we have industry part of this, of course. Actually, we have all the industry providers that are able to provide access to quantum computers through the cloud as part of this initiative, as partners of this initiative. Academia, of course, the research is extremely important, philanthropy and diplomacy involved. So first A is accelerating applications for humanity. What we will do here, what Open Quantum Institute has already started doing, is bridging UN organizations and their challenges to accelerate the progress towards the SDGs, and quantum computing specialists, quantum computing scientists, as well as the subject matter experts, so that we can collectively understand better what quantum computers are good for and how they can help with progressing towards the SDGs. The second key component of the Open Quantum Institute is access for all. So there, the work with the industry providers is what they have accepted to do is to donate time on their machines for Open Quantum Institute to then redistribute to researchers, developers, entrepreneurs, especially of quantum underserved geographies, to experiment on those use cases. At the moment, there's only private industry providers who have this capacity to give access through the cloud, but ultimately, the objective is to have also national systems joining this pool of capability that will be offered through the Open Quantum Institute. The third A is about capacity building and education, because if you have access to the machine but not the capacity to use it, of course, it's extremely, it will be a bit inefficient. So we have here a specific arm dedicated to education that focuses on the nexus between quantum computing and the SDGs, but also focuses on creating tools to help advance capacity building of diplomats and policymakers. And the last point is about activating multilateral governance for the SDGs. There, I would like to move on to the next slide, because that's the topic, the focus of today. What we have done here is we've initiated a dialogue with initially 20 permanent representations in Geneva, but also, of course, that dialogue has been then relayed in Capitol, informal discussions that bring together quantum powers, like I think most of the panelists here are based in countries that have quantum capability, but we have also in this group purposely involved countries that do not have quantum capacity at home. And that was very important because even if there is not a quantum computer in Morocco, in Mexico, in South Africa at the moment, those countries will still be affected by, of course, by the change of paradigm that might be brought by quantum computing. And with this group has wished to share the conclusions of their work. And at the moment, we are the report that is available online touches on human agency, digital divide, SDG applications, security, of course, security implication, the environmental impact, norms and standardization, where what the group has done is just to have a report that their wish was to have a report that states the state of play of the current international governance that can apply to quantum computing and the gaps that could that exist. But also what the group wanted to do is to take inspiration of what has been done in other domains. So I was very interested to hear about a few of those other domains that could eventually apply or serve as an inspiration for the governance to create for quantum computing. This has generated a lot of interest from nation states. We see that in international organizations and UN organizations, there's quite a few discussions that are starting. So there we hope that this group can also serve as a relay and an expertise hub to inform some of those discussions because it's multi-stakeholder by nature. And of course, we have a lot of hope in 2025 being named the UN Year of Quantum Science and Technology because we feel that awareness amongst policymakers, but not only, will be, of course, raised by such an operation, and that some of the work that we've done in Chamber can find a bigger resonance. Thank you very much. That's what I wanted to present today. I'm very happy to take questions if there is some.
I think for the sake of the time of today's dialogue, I'd like to conclude today's dialogue. But I just wanted to mention in the last phase, I hope you have more questions rather than answers, because this is the time for us to begin working together and start conversation on this really important topic. And I mean the UNIDIR, and along with the esteemed speakers here, would like to work with you. So hopefully we can work together in the foreseeable future, and have a great day. Thank you very much for coming again.